Okay, so we are on we're on the second group of questions. So we're still in pretty much chapter 15 stuff, okay? Simple harmonic motion, oscillations. This one says, what are the amplitude, frequency, and phase constant of the image on number 5 in your book? And I don't have an image to show you of that. Sorry, but you could go back and look at it if you wanted to and use this information. So the XO in that one would have been 10 centimeters. I assume that this is like a graph. So you would have to look at the graph and see where it's starting on the graph, and that would be your XO. And then of course, as high or low as that wave gets is the amplitude. So you have the inverse cosine of 10 over 20, which is equal to pi over 3 for your phase constant. So the amplitude for that particular question is 20 centimeters, and then the frequency for that particular question is going to be 0.125. So whatever your period is, of course, you got to do 1 over that. So that means that wave has to make a full wave or full oscillation in 8 seconds for that frequency to be 0.125 hertz. All right, sorry I don't have that one that I can kind of pull up a little bit for you, but I don't have the book available at the moment. And this next one says that an object is in simple harmonic motion, has an amplitude of 4 centimeters, a frequency of 2 hertz, a phase constant of 2 pi over 3. Draw a position graph showing 2 cycles of the motion. First thing that you're going to want to do, and really this is probably all I will show you what to do in here, is just to plug into this position equation, and then you could be able to identify, I think, then the graph. So the amplitude it gave you was 4 centimeters, and the angular velocity we don't really know, so we're going to have to find that. 2 pi frequency, we do have the frequency, so just 2 pi over 2 hertz. And, don't really need it because it wants this at, does it want it at 0 seconds? Yeah. So since we are just going to assume that this is 0, so since this is angular velocity times time, we really don't even need to do this. This would just be like 0 plus our phase constant here. Sorry. And then you're going to go through and do that, and it'd be -2 centimeters. So that's sort of like where that XO is. So whenever you see the graph, it'll start at like -2. And then since the frequency is 2 hertz, you could go through and find what the period was, which would be, 0.5 seconds. And so you would have to make one whole oscillation just be 0.5 seconds. All right, so you could start it like this and then go down and go up. And it tells you that the amplitude's 4, so that's where these are coming in. And, if it starts here, it's going to kind of have to end here, and this whole thing would have to be 0.5 seconds. And then you're going to have to go all the way and do another one for 1 second for it to be actually 2 cycles, because it does say 2 cycles right there. So you won't actually have to draw a graph on the test, but you might have to be able to identify one sort of like this. Okay, This next question says that a machine part is vibrating along the x-axis in simple harmonic motion with a period of 0.5 seconds and a range of 5 centimeters. At 0 seconds, it's at its central position and moving in the positive x direction. What is the position when t is 45 seconds? Actually, I think I changed this one to another one. Let me look on that and I'll get back on that one. Sorry. Let's go to this one really quick because I think that other one I changed to a different question. So this one says that a spring is hanging from the ceiling. Attaching a 500-gram physics book to the spring causes it to stretch 20 centimeters in order to come to equilibrium. So it wants us to find a few things. Okay, first, what is the spring constant? All right, so again, this is one of those vertical oscillation examples. So you have the same kind of thing that you did on a few examples before. So you have 0.5 kilograms times gravity and divided by whatever it stretches to, which is 20 centimeters or 0.2 meters. So your spring constant ends up being 24.5 Newton per meter. And then whenever you go to find, it wants us to find the period of the oscillation. So if you go through your equations, one of the equations is 2 pi times the square root of mass over k. So 2 pi divided by the mass, which is 0.5 kilograms, divided by 24.5 Newton per meter, which is 0.9 seconds. And then your V max is your amplitude times angular frequency. It doesn't give us angular frequency, so you have to do that K over M equation again, which ends up, I think, giving you I think it ends up giving you 7. So if you take 24.5 divided by 0.5, do the square root of that, yeah, it's 7. So you get 7 radians per second. And if you take that, divide or multiply by the amplitude being it tells you what it is here, this 10 centimeters. So the book is pulled down 10 centimeters and then released. So your amplitude is 0.1 meters times 7 radians per second, which ends up being 0.7 meters per second. Okay, and last one of this section is that a meter stick is pivoted about one end and allowed to swing back and forth with no friction. So now you've got a pendulum situation. So you should have some equations that are listed under pendulum. The mass of the stick is 1.5 kilograms and its moment of inertia is 10 kilograms per meter squared. If the period of the swinging stick is 5.75 seconds, what's the length of the stick from the center of gravity of the pivot? Okay, so first off, we've got, we have an equation listed that has the period is equal to 2 pi times the square root of our moment of inertia divided by mass times gravity times length. I do believe that you guys have that, or at least it wasn't an example that we did, so I'm fairly confident that you have it. So let's solve for length, okay? So kind of the first step here to get rid of this and then get rid of the square root. So that ends up making this period squared divided by 4 pi squared That is a mistake all the time. People put 2 pi squared instead of 4 pi squared. So try not to do that. We go through and solve for the length. We should get that length is equal to the moment of inertia let's see. We would have the moment of inertia divided by, oops, not that. So, if you end up putting all of that in, the moment of inertia is 10 kilograms times meters squared divided by, and you've got 1.5 kilograms times 9.5 meters per second squared times 5.75 seconds squared divided by 4 pi squared, don't forget the squared, should be equal to 0.81 meters. All right, this is kind of all in the denominator here. All right, so that's the second section, and probably just have one more video after that.